Steve Williams here from the Right Approach Consulting. I'm at American Standard Circuits, and I'm with Dave Lackey, the VP of Business Development, and also the resident expert on flex and rigid flex. Hey, Dave, how you doing?
Good, Steve. How are you?
So today we're talking about impedance, and impedance specifically for flex and rigid flex. What are some of the key factors that you have to control to hit the impedance values?
Well, impedance is always factored by your copper weight, how many ounces of copper you have, your line widths, and then your dielectric substrates, including what would be solder mask or cover layer.
Okay.
So those are your three key components, and dialing that in to match your customer's needs.
Okay. Is it a different? You look at it differently for flex than you would for rigid?
In some ways you do. First of all, you have to have a good modeling stack up, which is pretty standard when you're dealing with impedance. You have to, what's a little bit different about the flex impedance calculators is, for example, when you're talking about a strip line that's referencing a ground plane. We all look at ground planes as a solid piece of metal.
Mm-hmm.
Well, when you're talking about a solid ground plane in a flex that you want to bend, that's not fun.
Okay.
So what you have to make sure is your impedance model has they have a cross-hatching pattern you can put in there, and different variations of that. How much copper is left, how far apart are each lines that are cross-hatched. Okay. And when you simulate the impedance, because you want that bendability, you try to achieve that using a cross-hatch ground plane as a reference layer.
Okay.
It doesn't always work, but that's where you try to do that initially to make sure that you've got the flexibility you want, but you're not affecting the impedance.
Okay. That's interesting. I've seen your layup area when you're doing some of these projects, and the tooling is really interesting. You've had to come up with some unique tooling strategies. Can you talk about that a little bit?
Sure. So instead of having what would be considered a standard lamination plate for multi-layers, which typically has 4 holes on each end.
Okay.
When you're dealing with flex, that material likes to grow, shrink, move a lot, swim around. It's very thin to deal with, and trying to maintain good registration across that panel is difficult. So tooling plates with multiple tooling holes inside that can be used to accommodate each part where needed to support it, to keep it from moving is very key.
Now I've seen, I think we were talking earlier, I've seen some of your fixtures where it looks to me like you've got almost more tooling holes, you've got holes that are plated. How do you figure out how many you need? So
when we tool the job, you take a customer's individual piece or array and you stack it up multiple times in your panel of your choice.
Sure.
So all these holes in these tooling plates are affixed electronically in the CAM data. So when they go to do their stack up and put how many pieces on that panel, all those holes are present electronically and they see what they have. Then they will selectively go in, delete holes we do not want, and leave the holes we do in the file.
Okay.
And what happens is when you drill your flex layers, after you go through your etching and everything, we put it on a vision system, and it picks up optical fiducials to figure out, okay, this is where I am right now, because I've had some movement, but I'm going to drill now in this flex layer all of these tooling holes that are part of our plate. And we do the same thing with cover layers or any bonding sheets that may be affixed to that flex. Okay. So when we go to put it in these lamination plates, those pins are placed in place for all the layers to fit over, and all the bonding materials and cover layers to fit over to give extra support so you have less movement. So you're using the vision system to optimize the registration of all the different layers, just like you do in drilling. Exactly. Oh, same concept. Because you can't, obviously you can't have any kind of a hard tooling, let's say a post-etch punch machine, with all these possibilities of where we could put these holes. So that all has to be done on a CNC drill. So that's done picking up an optical target, and we make sure that we drill all those holes that are required into each of those layers or bonding materials. Sure. So you mentioned like the standard four position tooling. That's standardized to a panel size, right? But these are specific to a part number, correct? Yes, exactly. So, and then we have to drill additional maybe some sort of separator plates, typically aluminum, even FR4 sometimes. So, and it's all very unique to every part number.
Okay.
You think about when you're building flex, you're using a lot of disposable items like release papers, press pads, to allow the flex to conform with the bonding materials.
Sure.
All of that additionally has to be drilled and tooled to match just the specific part number.
Oh, that's fascinating.
So tooling can be a little expensive, and that's why.
Right.
You got to do some unique things with your tooling to accommodate the build.
And your guys' success rates are very, very high on this.
Right.
So, I mean, all the upfront effort in engineering and understanding all this stuff really pays off. I mean, it costs a lot of money, but customer gets good product that works.
Right. First time yield's important.
Yes.
You're on a timeline, obviously. Customer wants their parts. So you don't want to do it over and say, well, we should have done something differently.
Sure.
We try to make sure right up front we've done everything correctly.
Sure. So what about some of the constraints or concerns on impedance and this type of product? Because you guys do a variety of things. You do a lot of higher layer counts. You do what you call book binding.
Right.
You use some higher copper weights. What are the concerns with that stuff as far as impedance goes?
Well, like any other product, again, like I mentioned, copper weight, line width, and dielectric constant. What's nice about impedance in a flex application, you're dealing with low-profile coppers.
Okay.
So they etch a little bit easier. They don't have a real big tooth on it like you would want on something rigid.
Right.
So it's going to etch a little faster. You're going to get a better line definition. So understanding that when you're etching the flex is important. What's nice, and I found a lot of designers weren't even aware they could have impedance lines running across the flex portion, from rigid through flex back to rigid.
Okay.
But yeah, certainly, and the decay on flex materials is low, so it's a desirable material for dealing with impedance.
Sure. I imagine that you guys use pretty much every material that's out there and every manufacturer. Is there, do you standardize on a certain flex supplier? I mean, I would imagine they all have different properties as far as shrinkage and growing and stability. And
mainly when you're dealing with, we have adhesiveless flex, which means that it was basically the foil was fusion bonded right to the substrate.
Okay.
And you have adhesive flex, where you're using an adhesive material or like acrylic adhesive, binding it to the substrate and the foil at the same time. The properties there are a little bit different. As far as the raw materials go themselves, fairly similar. There's only a couple of different suppliers that we use.
Okay.
And again, what we can get here in the States, they typically can't get offshore, and vice versa. So we're limited in the amount of flex suppliers that we really have to deal with. The good part is once you dial in and understand the movement, you're not where it could be different from supplier to supplier, like you may see in rigid materials. We don't have that big of a selection, but it's also important to make sure you have a good inventory.
Sure.
Yeah, because if you don't, and right now flex materials a little difficult to get in some of the thicknesses and things. So by carrying a good inventory, you can accommodate the customer. You're not waiting weeks for your material to show up.
Is this type of product part of your quick turn capability?
Correct. Yeah, we have done some flex boards in as little as 3 days.
Wow.
Usually they're simpler ones, but there's a lot of times we may not be the cheapest guy in town, but we could do it quicker than anybody else, so we end up getting the order.
You can do it quicker and they work.
Right.
So yeah, I mean this particular market niche, I'm sure customers are willing to pay a little bit more for that, knowing that they're going to get something right off the first yield that's going to work.
Right, exactly.
Wow, and very, very interesting. You guys have a pretty unique operation here. You got a lot of talent here too, and for a company your size, you've got quite a bit of technical talent.
Correct.
So, I mean,
Correct.
the stuff you guys do just blows me away sometimes. I've seen some of your products on this, and they almost look like a wire harness.
Correct. That's very common. If you think about what's so desirable about flex, whether it be impedance or not, I mean, the fact that you can connect your boards together without using wire harnesses and connectors.
Okay.
It eliminates that. Then you got to figure what's the trade-off and the labor of taking a connector, cost, wire harness cost, and then somebody has to put it all together.
Right.
Sometimes there's soldering involved, reliability issues. That's where we see a lot of, I guess, product development in the industry of flex and rigid flex as to why people are going more towards that.
Sure.
It eliminates all the bulkiness of the wire harnesses and connectors.
And I would imagine it would probably give the customer a total lower cost of the product when you factor all that other stuff in and labor and, like you said, assembly and soldering and.
Yeah, it's close. You have to you have to do a one-to-one comparison depending on the complexity and how much of that you're eliminating. But from a reliability standpoint, far more reliable with a flex than dealing with connectors and.
I would imagine.
Right.
Yeah, and that's got to be a value to a customer. Okay, so we talked a little bit earlier about some of the constraints. Is there any type of a design that you've seen that a customer wants this on that you just said, that's just not going to work?
Well, some of the things you got to try to avoid is particularly where you have if you have even a impedance flex, obviously the way your lines run are critical. You see a lot of delay lines in impedance boards. So they're zig and zagging, and just because you need to have it so long in order for the impedance to work, not so desirable with flex. It's got to be a straight run because you're bending this thing.
Right.
You try to keep your traces parallel with the length of the flex. You don't want to go perpendicular because when you bend, you could crack.
Okay.
So from an impedance, I've not seen anybody with a impedance flex where they have delay lines going back and forth, just straight lines. So yeah, having that, I saw that, I'd bring it to their attention. There'd be some concern. And additionally, when you have plated through holes and you have a flex and a rigid interface, you want to be far enough away from that interface that you may not have an issue with a problem with that hole may being cracked because you're bending the flex there.
Okay.
Or additionally, you have some sort of typically no-flowing material, a non-flowing material, prepreg or an adhesive, so that doesn't squeeze out onto the flex portion. And if you do that, you got to cut it back a little bit. You don't want to have a void of laminate or bonding material where that plated through hole is, and that's a risk you would take if you had it too close to the edge.
Okay.
So again, that's something that we put in our book as far as guidelines and keeping via structures away from that interface.
Sure, that makes a lot of sense. We talked in an earlier session about bendability of flex, and we talked about bend radiuses and your book binder with different lengths depending on where it is in that stack up. Does that impact the impedance, the radius and the bendability and the different lengths of the circuits?
Not the bendability, the length, of course, because impedance lines are based upon distance. So having that figured, it would be a little bit more difficult, obviously, in a book binder because the lengths are different from each flex core. But that's all calculated in the design, too. So when you do your stack up to check your impedance, it already has that calculated into it.
Okay. That's fascinating. Well, awesome. Well, Dave, thanks for your time. Always talking with you and some of the other folks here, I just leave knowing how much I don't know.
It was my pleasure. Thank you.
Well, Dave, thanks a lot. So, once again, Steve Williams with Dave Lackey of American Standard Circuits, and thanks for watching.